Welcome. In this explainer, we're going to break down one of the most critical yet often overlooked interfaces in all of construction. We're talking about the structural joint and its really complex relationship with a building's MEP systems.
So let's just dive right in with a big question, one that every single site engineer has to answer. This really gets to the absolute heart of the challenge we're going to be tackling today.
All right, here's how we're going to tackle this. We'll start with why buildings need joints in the first place. Then we'll get into the different types. From there, we'll look at exactly how to handle HVAC, chilled water, drainage, and firefighting systems. And finally, we'll wrap up with the most critical takeaways. Okay, first things first, we have to understand the core problem. And here's the key. Buildings, well, they aren't nearly as static as they look. They're actually in constant subtle motion. We think of buildings as these solid, immovable things, right? But they're not. Every single day, they expand when it gets hot, they contract when it cools down, and over years, they literally settle into the ground. All of this movement creates incredible stress on the rigid pipes and ducts running through them. And if you don't manage that stress, you're looking at leaks, breaks, and even catastrophic system failure. So, if buildings are always moving, how on earth do you keep them from tearing themselves apart? Well, engineers design intentional breaks in the structure. Let's dig into the different types of these engineered joints that let buildings move safely. Let's start with the big one, the settlement joint. You use this when you expect different parts of a building to sink into the ground at different rates. Think about a massive heavy tower connected to a much lighter parking garage. They're just not going to settle the same way. And this diagram really shows you what we mean. A settlement joint isn't just a small gap. It is a complete and total structural separation. It cuts through the entire building, from the roof all the way down through the foundation, basically creating two independent structures right next to each other. Next up, we've got the one you're probably going to see on almost every project, the expansion joint. Its main job is to deal with all that daily expanding and contracting that happens because of temperature changes. And check this out. This is the key difference from a settlement joint. Notice how the separation starts above the foundation? That's because those temperature swings don't have as much of an effect underground, so you can often get away with a single shared foundation. And it doesn't stop there. Beyond those two, engineers have a whole toolbox of other specialized joints. You've got construction joints for when you pour concrete on different days, isolation joints to separate things like slabs from columns, and control joints, which are basically planned weaknesses to tell a big slab of concrete exactly where to crack as it shrinks. All right, so we've got the structural side down. Now for the really tricky part. How do we get all our MEP services across these moving gaps without them breaking? Let's start with HVAC and chilled water. For those big, low-pressure HVAC ducts, the idea is pretty simple. You have to put in a section that can actually flex, compress, and stretch right along with the building. We do this using a flexible duct connector, and it has to be installed at every single joint, no exceptions. And here's a perfect look at the solution in practice. On the left, you see the connector already installed on site, bridging the gap between two duct sections. And on the right, you can see the material itself. It's this tough, flexible fabric that's locked into metal strips, so it can be made to fit any size duct. Okay, but that's for air. What about high-pressure pipes, like for chilled water? A small leak in an air duct is one thing, but a burst water pipe, that's a whole different kind of disaster. For these, we need connections that are way more robust and are actually rated to handle the pressure. So here are a couple of the heavy hitters. On one side, you've got a braided stainless steel hose. That woven outside gives it incredible strength, while the inside is corrugated so it can flex. On the other side is a flanged rubber joint, which is amazing at absorbing vibration and movement. Both are engineered to handle serious pressure and movement at the same time. Okay, let's move on to two systems where you absolutely cannot afford a failure. Gravity drainage, which is crucial for sanitation, and pressurized firefighting lines, which, of course, are all about life safety. Now, for gravity drainage pipes, the ones that aren't under pressure but have to maintain a perfect slope, there's this really clever low-tech solution, and it all comes down to one magic number, 16 centimeters. So here's how it works. It's a super smart four-step process. You literally cut out a 16-centimeter piece of the pipe right where the structural joint is. Then you bridge that gap using two special slip couplings. What you've just created is basically a telescopic section inside the pipe that can slide in and out as the building moves. And this is exactly what it looks like all put together. If you're doing a quality check, this is what you're looking for, making sure that gap is sized right and that the couplings are installed perfectly before it all gets covered up. It's a beautifully simple and effective solution. Now, for firefighting systems, this is where the stakes are the absolute highest. The solutions might look similar to the ones for chilled water, but there is one massive difference. They have to be certified. We're talking UL or FM rated. This is non-negotiable. That certification is your guarantee that it can handle the extreme pressure and heat of a fire. And in some situations, you'll see these incredible flexible loops. These things are serious pieces of engineering. They're not just built for simple in and out movement. They can handle parallel shifts from side to side and even some rotation. This makes sure that life safety system stays 100% intact, no matter how that building decides to move. Okay, we have covered a ton of ground, from structural theory all the way to specific MEP parts. So, after all that, what's the bottom line? What do you absolutely need to remember when you're out there on a project? Let's wrap up with a pretty serious warning. This whole topic isn't just some small detail you figure out on site. If you get this wrong, the consequences are huge, ranging from annoying little leaks all the way up to a catastrophic failure of a critical system. And that leaves us with one final thought. We look at a structural joint and we see a gap, a division between two pieces of a building. But maybe the better way to see it is as a connection. The one place where structural and MEP engineers absolutely have to work together perfectly to make a building that's not just functional, but truly safe and resilient.